So who has their lab test today? Ooh, what time? 3? Does anybody have it right after this class? What about 7 p.m? Does anyone have it at 7? It's a bit rough, right? You get here at 9 and you've got to stay until like 8 o'clock. Anyway, you made it, well done. So if you remember from yesterday and a little bit in last week, we started doing differential equations, okay? And some of this stuff you've already seen in Math 1231 or 1241. But there will be some things that you haven't seen. Okay, so bear with me. So just to refresh our memory, because I know it's early in the morning, a differential equation has 2 things, an equal sign and a derivative. That's it. Okay, and like most equations, we want to solve them somehow, any way we can. Yeah? Now the difference with these equations is that you're looking for a function, not a number. You're looking for a function. Okay? And that function, yeah, you can check it, you can differentiate it, you can put it into your equation and you can see if it holds. Okay? So that's sort of the basic background. And yesterday we played a little bit of a game with classifying equations, right? So one type of equation for first order problems is called a separable differential equation. And so if that's what you've got in front of you, you can separate the variables and integrate both sides. That's probably the easiest, the entry level type of DE. Okay? Now the second type of problem we looked at was homogeneous or homogeneous, right? And for this one, you can use a substitution, okay? A substitution. Now somebody asked me yesterday if there are other substitutions that you can do with DEs, and the answer is yes, okay? So, you know, if you look here, this is sort of the general form of a homogeneous or homogeneous first order DE, and you make this substitution, and then you form a derivative, right? Okay? But if I look at, say, Mobius this week, you know, I was just trawling through Mobius as I do sometimes. Part B is definitely related to this first order homogeneous problem, but part A is using a slightly different substitution, okay? So you're even given the substitution here. Okay, so let's say you were given a problem like that. The process is almost identical to the case we looked at yesterday. You differentiate your substitution with respect to x. So here's your substitution. Okay, this is going to become dv dx, this will become 3, and this will become 5 dy dx. Okay, and then you rearrange that and you substitute out dy dx in the differential equation. So you get a dE in v involving dv dx. Okay? And then you solve it for v and then you back substitute. Okay? So the substitution method's pretty good. The stuff we looked at yesterday is a special substitution, v equals y on x. Okay? Now, it's always nice when you're told the substitution to use. Okay? But it's not always the case. Okay? It's not always the case. So sometimes you just have to work it out. Okay? But if it's homogeneous, then you know, oh, y on x, that makes sense, right? So that's the second class of problems we looked at. And you can see the actual solution is not very pleasant, right? The actual form of the answer is pretty unpleasant, but it's still okay. Okay, it's just that y is implicitly defined there through that mess. And remember, c is a constant. Okay, so that was that one. And then we had a bit of a flashback to 1231, sorry, and linear first order problems. I solved this one super easily. Part A is super easy to solve if you know the product rule. Okay, I just move things around and like, oh, bingo, it's the product of x times y on the left. Brilliant. Not always that easy though. So we bring this thing in called an integrating factor. Okay, so I could solve that one pretty easily. Yeah, but here's a bit more of a formal method for part B down here. So you look at the coefficient of y in the problem, and then you form what's called an integrating factor. Okay, you take that integrating factor, you multiply both sides of your original problem by the integrating factor, and you collapse the left-hand side to the derivative of a product. And that product involves your integrating factor and the unknown function y. Then you can integrate it. Great. We love it. Okay? So even if you're still a bit hazy on Math 1, 2, 3, 1, that's okay. You've still got time to get reacquainted with this. But I think it'll be in your... There'll definitely be some questions on ODEs in Mobius. Okay? And probably in lab test 2. Yeah? I don't know if it'll be as easy as this, but we will do some stuff that's new to you. Okay. All right. So what we ended on yesterday were these second order problems. Okay? Second order because they have the double derivative in the equation. Okay? And part of the motivation was, say, modelling a spring mass system. Okay? So you might have a spring and a mass, and it's attached, to a wall or something, and the mass is encased in oil, okay, or some substance that retards its motion, okay, or at least slows it down, okay. And so in this general kind of modelling sense, y is the so you can think, y is the or actually maybe it's better if it's there. It's going to hang under gravity, which is its equilibrium position, and then you perturb it, you pull it, or you push it, and you let it go. Okay. So basically, y gives you the position of the mass at some future time t. Okay. Now, in this model, A, B, and C have some physical characteristics and some physical interpretation. So, y represents the position, y dash represents the velocity of the mass, or the thing that's rotating, and A would represent the mass, okay, the actual value. So, this is a good way, I think, of connecting the stuff that you're learning with DEs to some sort of physical process. Okay, so B has got to do with the damping capability of the oil. So really thick oil, it's going to slow things down, right? Really thin oil, it's going to be able to move. And C is like a spring constant. So if C is really large, you'd expect the spring to be really stiff and it would come back close in a shorter time to like the equilibrium. Okay. So what about this F? Well, you can have 0 there, but you can think of F as being some sort of external force on your system. Okay, maybe you're tapping, or you're pushing, or there's a periodic push, something like that, and it keeps your system going. It keeps your system vibrating. Okay, so what will happen here? All right, so let's just forget about this for a second. Okay, let's just look at A, B, and C. Who can tell me what's the characteristic equation for this general system up the top? What is it? What will it be? The characteristic equation.
A lambda plus... No.
Yeah, you're on the right track.
Plus B... Sorry, A lambda squared plus B lambda plus C.
Yep, that's what you're going to say too, right? Yep. So the characteristic equation for this is going to be something like this. Okay? And so depending on the interplay between the mass, the spring constant, and I guess the viscosity of the oil, different things are going to happen. Right? Different things are going to happen. So remember, if we solve this from school, let's say we solve a quadratic equation, right? That's the form that you see at school. So are we going to get complex roots, real and unequal roots, or real and equal roots? What does it depend on? Depends on the coefficients, yep. Which ones does it, like, which part of this tells us whether it's going to be, say, real or complex? So if that's negative, we're going to get complex solutions, right? So our solutions will be in terms of, sine and cosine and times an exponential. If b squared minus 4ac is positive, what kind of solutions are we going to get? Yeah, real and unequal. Okay? In that case, we're going to have two exponentials driving things. Yeah? And what happens if b squared minus 4ac is 0? Yeah, one repeated root. Exactly. So we're going to get something like an exponential and, I don't know, x times an exponential or t times an exponential. That's going to change the long-term behaviour of our system. Okay? So a good question here is, well, how do we keep this system under control? Right? And I guess there's three cases to consider. They talk about over-damping, under-damping, and critical damping. Okay? So basically, over-damping is when things return to equilibrium very quickly because, you've got plenty of damping. Under-damping is when it takes a long time or there's some sort of steady state. And then critical damping is when b squared minus 4ac equals 0. That's just enough to suppress things. All right, so if you're asked about, you might be asked about this in Mobius, for example. I don't think you are, but I'll check. It just comes down to the coefficients in your problem under consideration. And using the quadratic formula, you can sort of go, okay, well, when am I going to get real roots? When am I going to get complex roots? When are they going to be real and unequal or real and equal? Okay? So, we've got 12 people at home. All right, so that's some motivation, but let's actually look at how we solved some of the problems yesterday. Okay? So this is sort of your standard way of doing stuff. You saw it in Math 1231. Basically, a starting point is, and you don't have to do this, but a starting point is assume solutions are of an exponential form. Now, the lambda here might be complex, but I mean, you know, you really don't have to consider whether it's complex or real because you don't actually use that bit in the solution method. Okay? So what most of us do when we're doing these problems is we look at the coefficients. So 1, positive 4, positive 3. You write down your characteristic equation and then you solve it. Okay? So you factor it and then you go, oh, in this case, the solutions are two real numbers that are not equal. Okay, so there's one solution, there's another solution, and you form a linear combination. That's your general solution to the problem. Okay? And then you can look at something like this. So look at the coefficients here, and suddenly it changes. Okay, now we've got two real roots that are both equal to each other. In that case, yeah, we can form that, but we can't do it again because we're not, you know, these two things are not linearly independent, as they say. So they're sort of a multiple of each other. So one way around this is to multiply through by the independent variable until they're no longer a multiple of each other, a constant multiple. Okay? And then thirdly, for this one, you know, lambda squared plus 2 lambda plus 5, here I've just completed the square, and in that case, you get two complex roots. Yes, question?
Why do you have to multiply by x instead of any other function for the second solution?
You can if you want to. You can try it. You can try it. Like you could try x squared if you wanted to, right? You could try it. But essentially, to show these two things are linearly independent, you can't go by a constant, but maybe you can choose a different function. The easiest function that we know of in terms of the independent variable is x. But try it, try x squared, right? Yeah, so we're talking a little bit more about that today, okay? We'll be talking a little bit more about that today. We'll be talking a little bit more about that today, okay? Sometimes you've got to say things 4 times. 4 times. 4 times. You've got to say things 4 times before people pay attention, okay? So, here, we're going to take this real part and this imaginary part and put them in here, okay? So this is standard from first year, I guess. Okay? All right. So here's the general picture. If you've got real and unequal roots, this is your form, real and equal and complex. You've got cosines and sines. Now, you can kind of justify the cosines and the sines being there because, you know, you can connect it back with Euler's formula, and when you do that, the coefficients or the constants could be complex. Okay, you can get that solution down the bottom out of that. Okay? All right. All right, question online. Okay, in part C, okay, deleted. They obviously worked it out. All right, so now, I showed you this forbidden method yesterday, okay? People were losing their minds. So instead of solving that, just annihilate the right-hand side to 0, okay? Annihilate the right-hand side to 0. So how can we do that? Well, you can differentiate both sides twice, yeah? So this will become 2 and then 0, this will become 0. So you get something like this, okay? Now for these higher order problems, 4th order, 3rd order, whatever, you can still use the magical characteristic equation, okay? So I did that. You've got that, you can factor, and then you can solve, okay? You get the standard solutions, and you get 2 others that have the same form as the right-hand side, okay? So in first year, when you make a guess, based on the right-hand side of equation A, 2x plus 3, I'll assume another solution, cx plus d. That's where it comes from. That's how it can be justified, okay? So you can use that method if you want to, but it's not super easy when you get to a problem like this. Part B's not super easy, because how can you differentiate that and make it 0? Does anybody know? I did ask this yesterday. Anyone at home? How do I differentiate 12e to the 5x and make it 0? Can I do it? Okay, what about if I used a combination of things to make it 0? What about if I differentiated it and then took away 60 times it? Would that work? Would it work? So what's the derivative of this? If I differentiate it with respect to x, what do I get? What is it? 60 times e to the whatever, right? So in theory, I could do that and then take away I could take away 5 times 12 e to the 5x. Okay, it's getting a little bit complicated now, so I probably wouldn't suggest it for a problem like this. So yesterday I said, okay, well, let's imagine that's 0, solve the homogeneous problem, and then we'll fit a particular solution to the problem, right? So this is, once you've solved it, that's the key thing. We're fitting a function that has the same right-hand side as the equation in part B. Okay, and when you can find C, then you've got an extra bit. Okay? All right. So there, that was it. So you basically add your homogeneous and your particular, works out. Okay. I think that's where I got up to last time, is that right? Yeah. All right, what about part C? Okay, let's have a look at that. I didn't do that yesterday, but can you see one thing in common with all the differential equations in here? They've all got the same left-hand side. Okay, so A, B, and C, the equations all have the same left-hand side. It's just the right-hand side that we're playing with. Okay, so what would we do here? For part C, let me see if I can squeeze it in. Okay, so for part C, again, you're going to have, this is your homogeneous solution because the characteristic equation is the same. But now we're faced with a little bit of a strange thing. Should I take this and fit this? Should I do that? No, why not? Yeah. Exactly. So you can see here, I've already got that in my homogeneous solution. So if I add these two things together, this bit's not adding anything new, right? So let's try what we saw in first year. And we multiply by the independent variable. If that doesn't work out, can anyone suggest what we might do? Yeah, multiply again. Multiply again, okay? You can keep multiplying until you no longer get the same thing that's in y sub h or any part of y sub h. Okay? So this is going to be a little bit annoying to differentiate because it's a product, but you know, we can do it. We can do it. Okay? All right. Yep. So if I was differentiating here, you're going to get a common factor of e to the 2x. So you're going to get sort of 2 plus 2x plus 1. Okay, you differentiate that again. Here's what I got. Okay? And then you would take those, put them into your differential equation, and get C. I got negative 10. Okay? So add y sub h, y sub p with p equals with c equals negative 10, and you've got your solution. Okay. So can you get A and B? No, not in these cases because we don't have enough information. If we had some initial conditions, then yes, we could do that. Yes, we could do that. Now, who can tell me, this was one of your questions yesterday, and I think I said the wrong thing, right? Back in part A where I showed you the forbidden method, right? We got that. And then you asked, oh, can we do something with the C and the D? Right? You asked that. And I think I said no initially, but actually we can. Can anyone suggest, if I'm looking at this equation here, and I have that, how can I get values for C and D? I've listed them here. Anybody know? Anyone know? Yeah, up the back. Yeah, it's YP, yeah. Well, yeah. So you're on the right track. Just say it for everyone at home.
Since that's YP, can we just differentiate it twice and then plug it into the...
Yep, exactly. So if you do the forbidden method, right, and you want to find the values of C and D, you can either just take this bit and sub it in here, you know, differentiate it twice and sub it in here, or you can take the whole thing, differentiate it twice and sub it in here. These things will disappear, right? So you'll be able to get C and D if you want to. All right, questions? Yes? Hang
on. For C, why did we use CX e to the 2x? Like in B, yesterday we just used CE to 2x.
Yeah, it's a really good question. So this is a really good question. I think it was going back to your question earlier as well, right? So let's look at B. Okay, so the first question I'm asking myself is, I look at this, so I'm just looking at equation B now, okay, so up there, all right? So I've got that solution, I add them together and form a linear combo, right? So then I look at the right-hand side. Is that the same form as that or that? Well, it's an exponential, but it's not e to the 2x or e to the 3x on the right-hand side, okay? Because if you do that and you say, oh, I'll just assume that a particular solution has the same form of one of these, then when you add them, the second part is not bringing anything new to your solution method. Okay? So you just need to be a little bit careful and go, okay, well, if it is contained there, I'm going to multiply by the independent variable x or x squared or whatever. You can just keep doing it until things disappear. Okay? That's a common problem that people make, right? And so how do you know if you've made a mistake? Well, one way is you try to find the C and you can't find it. You go, I'm going to find that C, right? And you differentiate and you sub it in and suddenly the C disappears. It's like, oh my God, what is going on? Yeah. Okay, so that's another good sign. You try to find a constant, you can't find it, you've probably made a mistake somewhere. Okay? All right. Everyone's quiet at home. How's everyone at home doing? Oh, hello. Hang on.
Yes. I might have missed this, but where did the C equals minus 10 line come from? In the one we're doing now.
Oh, yeah. So good question. So I haven't quite got enough space, but we've said let's fit this solution to this problem. Okay, so we're saying, hey, I want to find C. If I can find C, I know what that is, right? So I've differentiated it once, differentiated it twice, and subbed these expressions in here, right? You're going to get probably some cancellation, and then you'll be able to choose a value of C that balances it. It's called the method of undetermined coefficients. So C is a coefficient. You want to know what it is, sub it in and compare, and a value of C will come out. Yes?
I'm guessing we'd probably want to cancel some, like, x times e to the power of 2x then, or?
No, not necessarily. Not necessarily, because it's a good question. You've already got e to the 2x here, right? So if you cancel this off and you add these two things together, this thing will not be bringing any more information to your solution. You're just adding in another constant of what you've got. Okay? Yeah.
So we don't care, but if we knew the values of a and b, then
No. So even if you knew the values of a and b, you still would multiply through by the independent variable x. Okay? That's really good questions. What's happening at home? Come on. Is anyone still awake? This question goes to online and in the classroom. Still trying to understand, I get it. Let me know your questions. Okay. Yes. Wait.
I just could be misinterpreting, but I think what the previous person was trying to say is that when you sub in... Sorry? Yeah.
Sorry, yes.
Like when you put your y double dash, your y dash, and your y, like the particulars, into the equation, and you wanted to equate it to, was it 10e to the 2x? What you're expecting is that in your y dashes, your y's, there's an x term there, and it needs to be cancelled out in that equation.
Yeah,
so that it works.
Is that what you're saying? Is that what you're... Yeah. Algebraically, yes. Otherwise, C is 0, which is not what you want.
Yeah, and if it doesn't work, that's when you change to x squared.
Yeah.
And then x cubed.
You can do that. A lot of work, though. You'll be praying that you don't get that question in a lab test. Let's be honest, right? Let's be honest. Okay. So this is like, I know. So who did Math 1B last year? Anybody do it earlier than last year? When did you do it? Yeah. What about you guys? Did you ever do it? Term 2 this year? No, this year. Last year. You too? Okay, yeah. It's interesting to see how quickly we forget, you know? Like, I include myself in that too, right? Like, I try to learn something. Like, anybody use Duolingo here on your phone? Right, what are you learning? French, yeah. Anybody else? Duolingo? Right, yeah. What are you learning? Spanish, okay, great. So I use it, and gosh, I do about 3 minutes a day, right? Because that's enough to get through one lesson, yeah? Because I don't want to lose my streak. I've got 400 days, a 400-day streak at the moment, yeah, right? And so, I really want to do it. But a week later, a lot of the words I just can't remember, or I can't remember the grammar, or I can't remember the phrases or whatever. So yeah, I understand. Even though this is first year stuff, if you're not using it all the time, regularly, it's easy to forget. Okay? German. Yeah. German. Yeah. So I try I'm sort of, my mum's kind of half German, my dad's not. So I've always had a conflicted kind of childhood growing up, right? Thinking about identity. Am I German or not? Because the Germans don't accept, maybe it's a bit like some countries, the Germans don't really accept you unless you're born there and, you're a true German. So yeah. Anyway, that's another story. All right, so what's new? What is new about DEs that you're going to learn? Well, I'm glad you asked. Here's the bigger picture, and then we're going to move on to something that you haven't seen before. Okay? So, if you've got a non-homogeneous, different, and we're using this in a different sense from first order, which makes it doubly difficult, right? You fit a solution. So basically you solve this one, great. You fit a new solution based on the right-hand side, and then just add the two things together, okay? So can anyone tell me, why do you add these things together? Does anybody know? Why do you actually do the third step? Oh, hang on. Why does it work?
Doesn't the A, e to the, and then b, whatever, they cancel each other out so it becomes 0. So you're just left with the particular one.
Yeah, that's perfect. So this bit, because this bit satisfies that, if you sub that in, this whole expression into your differential equation, when you're differentiating, because this solves that, if you sub this whole thing into your problem up here, all of the derivatives of this disappear because they add up to 0. So that's one of the reasons why it works. Okay. All right, let's do something a little bit more new and a little bit more difficult. Okay? Variation of constants, aka variation of parameters. This should be new to you, unless you've done a differential equations course before. Finally, we're getting to something new. Okay? So, what is variation of parameters? It's a super amazing method, and we're going to learn it. So, I think I can motivate this through an example. Okay, this is something that you haven't seen in first year, and it's not really clear what you would do. Okay, it's easy to solve the homogeneous problem, y double dash plus 4y equals 0. That's easy. But what about this right-hand side? What about this right-hand side? So people would say, oh, just try something like, C times cosec, or something like that. Maybe you can do that, but there'll be times where, you get other stuff and you're not really sure what to do. Okay? Also think about trying to differentiate that so you get 0. It's also unclear how you would do that. Okay, so neither of the methods that we've learned are sort of directly applicable to a problem like this. So let me show you what this variation of constants, variation of parameters is. Okay, don't be shocked. I'll put this back up in a second, okay, so don't worry. Whoa. Here it is. Okay, so here it is. You've got something like this, and you can't fit a particular solution to the problem, okay? Homogeneous, yeah, no worries, easy, whatever. But fitting that second piece of information is not easy. All right, so here's what you do, and here's the basis of the method. Again, you solve the homogeneous problem, and you get these two solutions. They're both linearly independent. In other words, they're not a multiple of each other, a constant multiple of each other. Okay? And then what you do is you form this extra solution through this mess. Now, people get triggered when they see this. They go, what? What is that? I thought we're doing derivatives, not integrals. Okay, well, let's unpack it a bit more. Let's unpack it a bit more. Okay, you've got your solution from up here, in here. You've got the second linearly independent solution there, and they are multiplying by something. They're being multiplied by an integral each. Okay, so what's in the integral? Well, you've got the second solution, or the first solution, times the right-hand side and divided by this. Now, the W is just a function known as the Wronskian, okay? The Wronskian, named after a guy called, I think it was a man called Wronski, right? I might be Wronski about that, but sorry. But it's just a determinant, okay? It's just a determinant. So, you can think of it, if you want to, as something like that. Okay? Now, people freak out and they go, how am I going to remember that? And where does it even come from? And how do I know it's a solution? Okay? Well, good news, people. Good news. If I go into your, let's go into your, let me have a look. Yep. Okay, this is from last year. Okay. Huh? Back. Where's my Wronskian? I'm pretty sure that you'll get the formula for this, okay? There we go. Did I just go on that one? Let's have a look. If I get the cameras ready. Where are you? Please. Hey, okay. So it looks like the formula's not at the start of the test. It's buried in the test somewhere. Okay, that's it. Get a good shot. Okay, so the only difference between the formula that I'm putting in my notes and the formula here on the screen that you can see is that, you know, in this equation, the coefficient here is obviously 1, right? So A is 1. So in my notes, there's an A down the bottom here and an A down the bottom here, okay? So you don't need to worry about remembering the formula, okay? You don't need to worry about it. So it'll be, I think it'll be given to you, and you know, you just, it's more about applying it and knowing that it really is a genuine solution, yeah? It really is a genuine solution. So, yeah. But we'll talk about that. But at the moment, it's a bit of a mess, right?
What is A?
So have a look at the top differential equation. You see it? Yeah, it's a coefficient of y double dash. Yeah? Okay. All right. So that seems like a really strange format, right? But the key points is that to build this crazy particular solution, you need that and that because they're part of it. Okay? So it sort of goes back to solving the simplest case and then taking those functions and doing something with them. Okay? Doing something with them. Putting them into this formula. Okay? Questions? Now, in this setup, obviously the Wronskian, I spelled that Wronskian, yep. Okay, you can see the Wronskian is actually a determinant. Let me go back for everyone at home. Okay, so if the Wronskian's 0, what's happening here? You're actually dividing by 0, which isn't a good thing. Okay, so this will work as long as the Wronskian's not 0. Okay, if you compute the Wronskian and you get 0, then you've probably made a mistake, because in this course we won't give you a problem that really can't be solved. Okay? All right, let's have a look at home, see what's happening. Questions? What's so special? Ooh, what's so special about determinants? Good question. Well, determinants help us solve problems, right? You know, if we're solving a system of equations, we look at the determinant. Same sort of deal here. It sort of gives us a sense test about whether we can move things around and solve things, okay? So that's the way I remember it. And if the Wronskian's 0, then you know, you're in trouble. You've made a mistake somewhere. Okay? All right. Okay, another question. Because the DE is linear, so the sum of the solution is still a solution. Yes, that's correct. Exactly. Okay, so you don't need to remember this, but you do need to know how to apply it, and it involves some integration. Okay, so let's take a break. We'll come back in 10 minutes, and we will look at these variation of constants and parameters. So if you have any questions, come on down. Okay, everyone, let's get back to it. So, I've shown you a way of well, I haven't shown you yet, but I've flashed it up there, a way of solving these things through a whole bunch of integrals, okay? Let's actually do one and see how it works. And again, I'm just looking at one of the Mobius quizzes here. again, you're given the formula, right? So it's essentially just computing the components of the formula and putting it together, right? And then solving, a problem like this. Okay? So let's have a look. Okay. So let's compare this with the general form. And we'll work out A, B, and C. We'll work out f of x, and then we can do some stuff. Okay? All right. So here, okay, A is going to be 1, B is going to be 0, C is going to be 4, and the right-hand side is cosec, right? Cosec's 1 on sine, remember. Okay. So, in following with the bigger picture, we solve the homogeneous problem first and get 2 linearly independent solutions. And then we'll do something with them later. Okay? So let's do that. So the characteristic equation is going to be this. So we're going to get complex solutions, and they're going to be plus and minus 2i. Yeah? All right, in that case, when they're purely imaginary, it's just a linear combination of cosine and sine. Okay, so we've got cosine 2x and sine of 2x. Okay, they're going to be our 2 linearly independent solutions. So let's label cos of as y1 and sine of as y2. Okay, that's the easy part. Now it gets a little bit more difficult, right? We've got to take those 2 functions and put them into this big mess. Okay, so y1, y2, y2, y1, and then you've got the right-hand side and the Wronskian. But let's compute the Wronskian first. Okay, Wronskian's defined here. Or you can also write it as a determinant, which is fine. Okay, so let's do that. All right, the Wronskian is defined as this. Okay, and that's just a little bit of housekeeping, because if you're going to use the formula that is given, this crazy formula, you don't want to be dividing by 0. So it's just like a little check. You've got to compute it anyway, but you want to know that it's not 0. Okay, so usually with these things, you'll get a constant, but not always. Okay, a non-zero constant. All right, so that times that. So it's going to become 2 cos 2x times cos 2x. Yep, so that's the first part. And then minus that times the derivative of that. So that's going to go to negative 2 sine 2x. Okay? So if you look carefully, now you get cos squared plus sine squared equals 1. So the Wronskian's non-zero, so that's good. We're going to things are going to work out. We're not going to divide by 0, which is cool. And now we just need to put everything into this crazy integral formula. Okay? So let's write that down. What's that? Or have I mixed them up? So I've labelled y1 to be cosine and y2 to be sine. So we haven't got to the cosec yet at all. Okay? So we're going to get onto the cosec now. The cosec is that's your right-hand side, yeah? Okay? So we're just leaving that alone. Well, actually, we're going to do something with it now. All right, so that plus, and you just reverse the y1 and the y2 and you change the sign. Okay? So it doesn't look too bad if you eliminate the variables. It looks all right. It's still not sure where that comes from or why it even works. We'll get to that. Okay? So let's take our Y1 und Y2, our Wronskian, and our other parts and dump them into this expression and see what happens. Now, we are going to have to do some integration, but hopefully we can handle it. Okay? All right. So, all right, A is 1, so that's good. W is 2. Y2 is sine of that. And I'm going to multiply by cosec. All right, oops. So it's not looking great at the moment, but have I got that wrong? Is that integral very difficult? Why not? Hang on.
Because cosec is 1 on sine, so sine times 1 on sine is just 1.
Exactly. So I was a bit worried for a second there, but actually the two bits are going to cancel each other out. Yeah? So that's good, right? So remember this is just that, okay, like you said. So this will actually cancel each other out. Let's look at this bit. Okay, y2 is that. y1 is that. Okay, so let's write it as cosec again. Okay, so that's going to simplify nicely, and I'll integrate it to be so it'll become x on 2. Okay, and now it's about this thing. So what can we do here? Let's use this again. So that bottom integral doesn't look great. But is there a strategy that we can do to knock that bottom integral over? It's the integral of cosine on sine. Yes. Oh, good try. So inverse tangent probably won't work, but it's good to try.
Just the ln rule?
Yeah. What do you notice about the relationship between cosine and sine, or sine and cosine? They're like derivatives of each other up to a minus sign, right? So you've got something that is kind of that is the derivative of that. Yeah? So you can use substitution if you want to, or it's just the logarithm of the denominator. Okay? It's the logarithm of the denominator. Okay, so if I do this, oh, I'll get something like that. This thing will go to something like that. And if I differentiate this, the 2 comes to the front. So I want to somehow control that. Okay, so it's a quarter sine of 2x all multiplied by natural log of that. Oh, and I should put absolutes in there too, because I don't know whether it's positive or negative. Okay? Now, I don't need to worry about constants of integration. In this case, it's just a particular solution. Okay? So that's it. One of the integrals was easy, one took a little bit more thought. All right? So the solution then it's going to be a linear combination of these 2 things plus that mess. Ooh. Can you see how it's getting a bit more difficult now? Maybe just a bit longer. I don't know if it's that much difficult, but maybe just a bit longer. Okay? So, fear not, you're given the formula, which is great, because nobody can remember that. And in fact, it's quite difficult to derive the formula, to come up with it, but I will show you why it works. Okay, because people are like, well, how do I know that works, right? I'm happy to show you that. But before I do that, questions. Questions. Okay? Usually, these 2 things are, they're manageable in some sense. Yes.
I just wanted to verify, so with y1 and y2, they're like the 2 parts of your solution to the, what do you call it, the characteristic, sort of? Yeah, homogeneous, equation. And if, for example, our exponential wasn't cancelled out because of the lack of a real part, would that also be included in your y1 and y2s?
Yes.
Right.
Yeah, so hang on. So yeah. So this can get a bit crazy, right? Because if there was another term in there, and you could have, e to the negative x times all of that, e to the negative x times all of that, and then the integrals get a bit crazy, right? Yeah. But the Wronskian sometimes saves you because there might be the exponential here, but there's an exponential hiding down here.
Oh, okay.
Yeah.
Thank you.
Hmm? All right. Well, we need a little drone to take it around, right? That would be good. Somebody get a patent pending on that, right? That would be good. Okay, I'll think about that. Okay, so now here's a really good question. With this amazing knowledge, which I'll show you why it works in a minute, can you go back to these sort of questions and do this new method? Okay? Yes, you can. Okay? You can. So the difference that I can see between, fitting the solutions for the right-hand side and this new method, it depends if you love differentiation or integration. If you love derivatives, the OG method's better. If you love integrals, the new method's better. Okay? Now, here's a quick survey. Everybody at home as well. Who thinks differentiation is easier than integration? Can I have a show of hands? Who thinks it's easier? Anybody think integration is easier? Oh. You're in the minority though, so. But I think this is what people think, right? Why do you think integration's easier? It's a good question. It doesn't have to have an answer, like a definite answer.
I feel like I screw up more with differentiation. Like I make a bunch of silly mistakes, but integration seems cleaner.
Yeah, okay. That's cool. That's cool. They are just reverse processes, so I get it. So if you love derivatives, these sort of problems can be solved by fitting a function or fitting a curve to it, right? If you love integrals, what do you think of this new method? What first thoughts? I haven't told you why it works yet. The drone. Well, let me know. Because when I first discovered this, I'm like, I'm going to go back and do all those problems using this new method. But it's actually not that simple, right? Because the integrations get hard or harder. Okay? All right. What are people saying at home? Ooh. Integrals are cursed. Differentiating is great. Yeah? Well, I don't, it's fine. I'm not going to argue with that. It took a long time for people to understand that derivatives and integrals were the opposite of each other. Did you know this? So back in the day, all the, Newton and Leibniz and all these sort of legends, they had integrals over here and they had derivatives over here, and they didn't know that they were just the opposite, right? It took a long time for people to work that out. I don't think there's any exponential in this answer. So there's a question at home, but there's no exponential in this answer. All right. So why does this magical method work? Well, I'm glad you asked. I'm very glad you asked. Let me see if I have something here about it. Yeah. Okay, yes. So you don't have to write this down, but this is just my scratchy writing from, 6 a.m. this morning. So the way I justified it to myself is I said, right, this mess, just differentiate it and shove it into the top differential equation and show that you end up with f of x, whatever f of x is. Okay? So what do we know? If we're differentiating this, what rules are at play? You can tell me. If I'm differentiating that crazy form of y sub p, this crazy form, what? Because you guys love differentiating, right? I have the data on that. Maybe not so much for you, but what? If we're going to differentiate that mess, what rules do we need to be aware of? How would we do it? Somebody, anybody. Product rule, who said that? You rule. Product rule, right? Because this is a function of x, that's a function of x, this is a function of x, that's a function of x. What else? So definitely the product rule. What else? So I do the product rule, what happens? I do the product rule. What happens? I get a bit of cancellation, but also I'm differentiating an integral. So what's the idea there? FTC, you're down with FTC, fundamental theorem of calculus, okay? If you differentiate an integral, things disappear and you just get what's inside, usually, okay? So here's the product rule. You get the integral missing or disappearing, and those things disappear, right? So even though you've differentiated it, it doesn't look too bad. But when you differentiate it again, using the product rule and fundamental theorems, it starts getting a little bit crazy. But there's hope. You've got this and this, common factor of f and all that. If you factor this, what's this mess up the top? Oh, it's exactly the Wronskian. Okay, so this term and this term go in there. Okay, all right, so we've got some simple thing for that, that, and that. Let's take those three things and plug them into the left-hand side. We want to get f. Okay, we want to. So if we do that, there's our three messes. We can place all the y1s together and all the y2s together. Now, what's y1 and y2? They solve the homogeneous problem. Okay, they solve the homogeneous problem. So I'm going to team that up with that, and then these three together. Okay, who can tell me, people at home, what does this equal? Anyone? And what does that equal? Anyone? Oh, whoa, got to go up. Come on, make my day. Why have I clumped all those things together with the y1s and the y2s? Yeah, 0, exactly. So you're saying because y1 solves the homogeneous problem, that mess is 0. What about that? 0. So boom, boom, what are we left with? F. Wow. How good is that? Okay, so it's a freaking mess. The original form is a mess. But you can justify that it really does give you a solution to the non-homogeneous problem. Okay? The deeper question is, where does the original form come from? Okay? And I'm telling you, it's not easy. Right? It's got to do with something called a Green's function. Anybody heard of a Green's function? I'd be pretty impressed if you did. Green's function. Oh, really? I don't understand it. Oh, it's okay. Yeah, that's good. ChatGPT's learning a lot now, right? I'm training it every day. Are these solutions correct? Where have I made a mistake? I need to teach this tomorrow. No, yeah, Green's functions, you'll see it probably in third year if you do some more maths, right? PDEs, stuff like that, partial differential equations. So the best I'm going to do in this class is I'm going to verify that actually that mess is a solution. Okay, but I'm not going to derive it from first principles because it'll just take too long, and I don't think it's very easy to do either. Questions? Questions. Let's have a look at home, see what people are doing. Oh yes, exactly. So this is excellent. This is an excellent comment. All right, ChatGPT used Green's theorem to solve flux in a field questions. Yeah, so this goes back to when we did vector calculus and we did double integrals and line integrals, right? There is a connection between double integrals and line integrals, okay? So it's called Green's theorem. It's amazing, but not part of this course. It's still cool though. It's still very cool. And if you look at my videos with the notes, I do talk about it very briefly, because I love it so much. Okay? Other questions? Now you can see that if you stuff up the original part of the question, there's no real coming back. Okay? Where are we? Okay? If you stuff up the y1 and the y2, well, you're going to use them in here. So you want to make sure that they're correct. Let me just go back for everyone at home. Okay? in this formula, they depend intimately on y1 and y2, the solution to that original homogeneous problem. Okay, so don't stuff it up. So how can you tell whether you've got the right solution or not? Test it. If you have time, test it. In a lab test too, you're probably not going to have time, right? But prove me wrong. Prove me wrong. All right, should we do another one? Let's do another one. Sec x. I'll just show you the one that I did before. Okay, so now we've got y double prime plus y equals sec x. So it's a little bit difficult because we haven't seen anything like this in first year. It would be tempting to say, oh, my particular solution is going to be a c sec x or something. You could try it. I don't think it'll work out for you. Okay? And why don't I think it'll work? Well, let's have a look at the solution to our previous one. Where are you? Yeah. Okay. Although this is kind of, that is kind of related to that, you've got this hanging in there as well. So I don't think you're going to get much joy if you try to apply first year techniques in here. But you might. Sometimes it works, but not always. Okay, this will work always. All right, so you're given this problem. In this context, we've got y1 and y2 are going to solve that equals 0, and my right-hand side is sec x. Okay, so if I can write down the homogeneous or the characteristic equation, it's going to be lambda squared minus plus 1, right? So lambda squared plus 1 equals 0, so that means lambda is going to be plus or minus I. In that case, we're going to get a linear combo of sines and cosines. So let's say, I don't know, y1 is going to be cosine x, y2 is going to be sine x. Okay, from those two friendly functions, we will build this monster y sub p. Okay, we will build it through these integrals. Okay. All right. So let's do that. Oh, I've written it down here. Okay. So let's look at the Wronskian. Here's the Wronskian. I've computed the Wronskian, taken the derivative, applied the formula, and the good old chestnut cos squared plus sine squared equals 1. Yay. Okay. So we're okay here. We're not doing any kind of division by 0. If we were, it would be a problem. And so now it's time to roll out this amazing form. Okay? All right, so let's do that. Now remember, sec x is just 1 on cos, right? Let me make this a little clearer. Okay? Sec x is just 1 on cos. So I think this is going to be similar to the previous problem where we're going to get a little bit of cancellation and we'll have to do something else. Okay? So that's going to be okay. I think that's going to simplify, but this is not. All right, so now we're faced with the same thing that we had in the previous question, the logarithm of something when we do the integral. Okay? So what do we notice about the relationship from a calculus point of view between cosine and sine? It's kind of the derivative. They're the derivatives of each other up to a minus sign. Okay? So who can tell me what's this integral going to be here? The first integral. Second integral is easy. What's the first one going to be? Who can tell me? Who can tell me? What's it going to be? Yes, or almost. Yes. So this first integral is going to be the logarithm of cosine, and you just adjust it with a negative sign. Okay, there's a negative sign out there. Yes. Okay, that's just going to go to x, and then I get something like this. Okay, now notice that form isn't intimately connected with that. Okay, so I don't know how you would solve this using first year techniques. Maybe you can do it. Prove me wrong. See if you can do it. Ask ChatGPT. Huh? Is there anybody here using what is it? DeepSeek. I was about to say deep fake. Hey, DeepSeek. I'm getting a bit tired now. DeepSeek. Anyone using it? Anyone using it? Anyone? People are using. I'm using ChatGPT. I haven't used DeepSeek yet. I have used the previous incarnation from CCP, which was called Ask Eric. Do you know about this? Have you heard about this? Ask Eric was very interesting with the answers. What about Copilot? Anyone use Copilot? That's the UNSW official one, right? Yeah. Yeah. Yeah, you have it. Right? So Copilot, what's your experience, like your position on Copilot versus some of the others? Yeah.
Copilot is amazing. Yeah. It's very convenient. It's just built in.
It's good for maths too, right?
Yeah, you can just like highlight the text, right click, and just press Copilot.
And is that on Edge? Is it a browser? Yeah, Edge. I haven't got to Edge yet. Yeah. But Copilot's all right. For me, it is the official UNSW sort of program, right? So I feel maybe a bit less guilty. But with DeepSeek, we have all these instructions not to download it, not to download it, because security and all that sort of stuff, right? I think the university's paranoid about all sorts of stuff. So, all right, that's my Y sub P. Grok. Hang on, let me put this up. Grok is the best for math and coding. Grok? Am I gonna regret this if I do a search for Grok? Oh. Okay. Of what?
Ask it what it thinks of Elon Musk.
Okay. Why is it in German? Oh, but now it's in English. Okay.
Yeah, that's definitely
Is it? So this is the simping. Even the Germans love a good simp. I wonder if it comes out of Germany. Is it? Okay. Oh, what's your take? I love that when they answer a question with another question. It's like, I don't know what to say. What do you think? Yeah. Wie kann Grok helfen? Oh ja. No, my phone is though. My phone is.
just like this is unrelated to your agenda.
Yeah. No, I switched my phone over a few months ago, but I haven't done it with the browser yet. Those German keyboards are weird too. Hey, who was doing French? French keyboards are weird too. It's like all the letters are in the wrong places. All right. Okay, so I will check out Grok. Thank you for the suggestion for everyone at home. Grok is the absolute best for math. That's quite a statement. I'm going to try it. All right. So, let's put our... You've only got like 15 minutes left. Yeah. Are you in the next class? Okay. So just pretend like you're paying attention. Is that okay? Yes. We're just learning about AI and Grok. All right. So, if I was solving this differential equation, I've got y sub p. The homogeneous solution was easy. So you just put them together. And it's a mess. And this doesn't look much like that. Okay? So this is a danger if you want to do first-year techniques. I love first-year techniques. But if you want to do first-year techniques on these problems, it's probably not going to work all the time. Sometimes it will, but it won't. Maybe we should ask Grok about that. Questions? Okay. Yeah, so it's a bit of a mess, right? Yeah. Okay. All right, are there any... So, who's done the exam, lab test 1? Who's done it? Okay, so is anybody angry about the test? You're angry? Oh, tell me about it. What happened? Are you all disappointed?
I had to find the second derivative of tan and x to the power of 3 y squared, and that wasn't in any of the lab test or questions.
Wasn't it?
It wasn't. It was only sine and cos.
Oh, you could have written it as sine over cos, though, I guess. Like you could have written tan as sine over cos. Let me check that. Because if that's not there, then maybe it's a problem. Do you want to send it to me?
I can't access the question.
Just as best you can remember. I can look it up on the system.
For the D test, I also got one that had the mixed derivatives were not equal, which I didn't think we could get. But there was it was x squared plus 2xy, and then there wasn't a y squared term.
I'd be super concerned if you were getting problems where the mixed derivatives didn't equal each other. All right, send that to me as well. Yeah. Any others? Any other people want to have a whinge? Huh? Lab test 2, yeah. If you've got an idea of how to make it better as well, like that's also appreciated.
How did I do button? Like, because at the end of the day, like it stops you from guessing.
Yeah.
But it still means you can get rid of like formatting errors.
Yeah. How did I do is still going to be there in lab test 2, but no, it's not unlimited. So you can do it once per question. Okay. Again, not my decision, but at least it's something. It's better than first year, right?
This might be related to the last one where the mixed derivatives didn't equal, but I think on one of them is like exponential x squared plus y squared over x squared, and the y squared that is on the exponential is a little ambiguous.
Yeah.
So I initially thought.
Yeah. So in fact, somebody asked this in, I think it was the second lecture of the term, and I said, oh yeah, it looks like it's a coefficient, but it's actually up in the exponent. Yeah. So if you're not sure about the typesetting, I would just put my hand up and say, look, this is unclear, can you, you know, I don't know how to distinguish this, right? Yeah. What about people at home? Yes.
I mean, I just like to have a preemptive whine about how I've managed to schedule my exam in such a way that I have classes right before and after it. So I just have to teleport in.
So my advice is, if you have an assessment after a lecture or a tutorial, just tell the tutor or the lecturer and just leave, right? Like, I know sometimes I'll point somebody out leaving, but if it's for a good reason, you know, I mean, like, a test is more important than a lecture, let's be honest, right? Let's be honest. All right. Okay, hope everybody has a great day. Good luck if you haven't done your test. Come down if you have a few more questions. And we've pretty much finished differential equations now, okay? At least ordinary differential equations. On Friday, we'll do a couple of revision questions and a few other things. So hopefully see you then. Good luck. And by the way, I've been looking at the marks for for lab test 1 so far. The average is pretty high so far. The average is about 30, okay, out of 35. Standard deviation about 8. So, all right, folks, see you.